It's officially starting time for our first event of the year for Engineering Tomorrow. Thank you for all of those who have joined on time and are ready to roll today for our water treatment lab day. We have the amazing Dr. Eric Einstedt here today. He is the architect of Engineering Tomorrow. And I'm not being, I'm not trying to overstate it. It's literally true. This is his program. So we're going to start with the founder of this lab program with Dr. Eric Einstedt from GIP. He's going to introduce himself. Again, please do not hesitate to type in chat if you have any questions. Do not be shy, and let's get today rolling with the introduction to water treatment and Dr. Eric Einstedt.
Well, thanks a lot, Monica. Boy, I don't know if I can live up to all that introduction from everybody, but I'll do my best. So anyway, again, I just also want to say thanks so much for joining our first special lab day of the school year. We're going to be, this has turned out to be a way that we really enjoy engaging with you students and the classrooms. We like it so much that we've now scheduled 2 a month. So we're going to be doing these throughout the year. And we hope you'll enjoy the one today. Today's lab is actually one of our original labs. When we started with Engineering Tomorrow, we started off with wind turbines and water treatment. So water treatment's gone through a lot of changes as far as the lab goes, but it is our original lab, and it's still just as applicable today as a problem that engineers need to solve as it was, 8 years ago when we started Engineering Tomorrow. So hopefully you'll get a chance to learn a little bit about why water is such a critical problem, and clean water is needed. And basically you'll learn a little bit about how engineers are part of the solution of providing water to humanity. And it's going to be a continuing issue. So just to give a quick background, as Monica said, my name is Eric Einstedt. I'm a chemical engineer. I was trained and went to college at Cornell and then University of Minnesota in chemical engineering. And then I worked in GE, a company called GE, which you may have heard of. And part of my time at GE, I actually worked in the GE water business. So I was actually working in the business where we would sell services, water services and water equipment and water treatment chemicals to companies. Since then, I was with GE for a while, and then right now I've been working now for a company called Global Infrastructure Partners, which is an investment company, and we invest in infrastructure. And usually the water treatment and all the facilities that provide clean water are considered infrastructure. And you're going to hear a lot more about that towards the end of the day, because we have an excellent speaker, Natalie Selmo, an engineer who works for an organization called Engineers Without Borders. And that organization works globally, but she works specifically around the United States to help communities essentially build out infrastructure that they need for their areas, their communities. And she said that you'll hear most of what they do is actually water related. So you can look forward to that and look forward to hearing about her studies and why she got into engineering and the kind of things she does as a practicing engineer. But let's get started on water treatment. So just give me a second here. I need to share my screen, and I need to actually create a slideshow here. So now I've lost you all. So let me try to find you again. Let's see here. Give me a second.
No worries. We're all here, Eric.
And I also want to make sure I share my sound and optimize for video. And that could be the one. Can you see that? You guys see my
Yes,
my
we
screen?
can. Yes.
Okay, great. Okay. So let's talk about how water treatment works, and what's included, and why this is so important as a problem that engineers to work on. And then what we're going to do is if you haven't been involved in any of our labs, we're going to give you a little background of the technology around water treatment, how engineers contribute to this industry, and then you're going to get a chance to actually do some engineering yourself, and you're going to build a filtration system for treating water. So water treatment, as you may or may not know, our breakouts are all developed by engineers, and as I said, this is one of our original breakouts. Edgar Martinez, who is a civil engineer, trained as a civil engineer, and actually I think now he's working as a teacher. Was one of the key leaders of developing this breakout. And you can see Mona and Caroline. At the time, they've graduated by now, but they were engineering students and helped develop this breakout. So let's start thinking about water. I think you probably have heard about your carbon footprint. That's the kind of, the footprint of the things that you do that releases CO2 in the atmosphere. But have you ever considered what a water footprint is? So water footprint is basically your use of water during the day. How much water do you use? And you should think about other than the water that you drink, and which is important for your health and everything, where else is water being used during the day, the things that you use? So the water footprint is basically the total volume of fresh water used to produce what you consume, and the goods and services you consume. So think about how many times have you used water today? So I think if you think about, what are we at? We're in, mid-morning here. You probably got up. I hope you brushed your teeth. You probably washed. Maybe you had a shower. Maybe you had something to drink for breakfast. Those are maybe the things that water you think about using. But there's a lot more other places that water is being used. Now, what you'll find is that most of that water is fresh water, and the amount of fresh water on the earth is a very small fraction of the total water. So the fresh water is, there's a lot of water on earth. Most of it's in the oceans, and the ocean water is got a lot of salts in it. There is fresh water. There's like 3% of all water is fresh water, but a lot of that fresh water is not accessible to us. A lot of it is tied up in glaciers. And yeah, I know the glaciers are melting, which, is not good. And the problem is the melting glaciers are going right into the ocean, so they're turning into water that's not very usable anyway. A lot of the water, the fresh water, is underground in aquifers. And that's hard to access. But if you have a well and you get your water from a well, that's where that's coming from, underground aquifers. The fresh water that's more accessible is actually in rivers and lakes. But again, that's a very small percentage of a very small percentage of all the water on the earth. So it's really a challenge. And what's critical about water is that it has to be fresh to be most useful. It has to be clean. It has to be something that doesn't have contaminants in it that can make you sick if you're consuming it. And we'll talk about what some of these contaminants are. The problem with water is also, the basis of life. So a lot of life lives in water, and that's not necessarily good for you. So let's do some basic grounding of volumes. Can you think about how many cups of water are in a liter of water? This is just to give you a kind of a scaling of things. Think of a cup, think about a liter. How many do you think there are? Second of all, how many cups are in a gallon? Now, maybe you know this. This is an exact number, because if you think about cups to pints, pints to quarts, quarts to gallons, you might be able to figure out what the number is there. And then think about how much water do you think it took to make your morning coffee, your morning latte, whatever if you had like a hot drink in the morning, how much would it take? Just take a guess, and you might be surprised at the numbers. So let me tell you the answers to these. There's about 4 cups in a liter. There's about 16 cups in a gallon. And if you think about all the components that go into that morning hot fancy drink that you buy at Starbucks or at Dunkin' Donuts, there's 190 liters of water that goes into that. And you may say, that's crazy. Why? Well, it turns out that cup, the paper cup, to process that cup takes water. The little holder on the outside of the cup, keep you from burning your fingers, that takes water. The plastic lid takes water. All these things are adding up. The milk actually takes a lot of water. I mean, I know it comes from a cow, but the amount of water that it takes to raise cattle and manage cattle is actually a very large amount. So let's see a short video that talks about water and the use of water and some of the problems of water. And as you're watching this, just think of 3 things that you learned, that you're learning in this video that you may not have known before. All right. So just as a just to let you know, you saw at the very end, this video was made by a company called Xylem, which is one of hundreds and hundreds of different water companies around the world. They do a lot of work on the measurement of pipe flow, kind of the digital management of water systems. They use a lot of AI and a lot of technology, but they're not the only water company. There's also companies like, as I said, GE Water used to be, was sold to a company, and there's a company called Suez that's well known, Veolia. There's American Water. There's all kinds of companies that manage water. A lot of the water companies in the US, or a lot of the water treatment in the US, is actually run by the governments. So local governments will run their water systems. But think about, are there 3 things that you learned from the video that surprised you? A couple of things that you might have come across. First of all, you may know that there is a lot of water, but very little of it is fresh water and usable. Did you ever think about that? We take perfectly clean drinking water, and that's what we use to flush our toilets. That's such a waste of good, clean water. It doesn't have to be that clean. The property of water that we use in your sewage system doesn't require that you can drink it. So that's, that would be a way, because to create very clean water and drinkable water costs money, and you could reduce the cost of that. Another thing that you may not have known from that video is a lot of fossil-based power plants. So if it's a electrical plant that's producing electricity, if it's a coal-based plant or an oil-based plant or gas plant, a lot of those plants require water. In fact, I mentioned I used to work at GE Water. One of the things that one of our best customers was nuclear power plants, because they needed ultra pure water. And I mean, water with no oxygen, no dissolved gases, no nothing in it, to run their steam turbines. So that is a big source of use of water. And as we go to more and more renewable energy, they don't need water, don't use water in wind power or in solar power. And then the other thing that you may have noticed is how much leakage there is. I don't know if you saw the numbers. In London, about 40% of the water that they have in their system is just wasted by leaks. And can you imagine how much savings that could be if they could just fix the leaks? They wouldn't have to process as much water. So hopefully that video gave you a sense of some of the things that are critical in water, and what are some of the ways you can reduce your water footprint. Obviously, you could use less of these things that require water. Think about just drips. Do your faucets drip? That over time is a loss of water. But also think about other ways that maybe you can lessen your footprint. Now let's talk about what are the things that makes water contaminated, and they can really be classified into three different areas. So the first one is what we call suspended solids. It's basically chunks of stuff, like dirt or little bugs that are dead, or anything that actually doesn't dissolve in the water. So you can see the picture. Usually you can see suspended solids. And the way you get those out of water is basically by filtering it out, or screening it out, or settling it. And when they say settling, what they mean is if you have suspended solids in water, if you just wait a little while, the suspended solids typically will fall out, and they'll fall on the bottom, and you'll have cleaner water on top. So in your work this afternoon or today, when you make your filter, you're going to be trying to remove the suspended solids in the dirty water that we make. The second type of material that contaminates water is the dissolved materials. So this is like the ocean, right? The ocean looks like it's clear, but we know that if you taste it, there's a lot of salts in it. So these are the like sodium chloride that's dissolved. If you have hot tea, which I have here to try to keep my throat good, if I put sugar in it and I stir it up, the sugar disappears, right? It's dissolved, and these are much harder to remove from water, but they can be removed by some processes called water softening, ion exchange, something called reverse osmosis, where they're pumping the water through a membrane. And then you can also dissolve gases and things in water. That's also dissolved materials. And that can be removed just by letting the gases, aerate. You can get them out, de-aerate them, and putting adsorption filter there. So that's dissolved materials. The third category is the category that really makes water dangerous to drink. And that's the category that has all the microorganisms in it. So these things that you can see, the protozoa and the bacteria and the viruses, they're happy living in the water. And they're just as happy if you drink them living in your stomach and then making you sick. So the way you it's hard to remove them. Some things like reverse osmosis can remove these types of very, very small living things, microorganisms. But typically what you do is you try to kill them. So you can do that by adding chlorine, by ultraviolet radiation, and or treating them with some other types of chemicals. So water treatment and making clean water requires that you do different types of things. And it's typically a multi-step process. And typically you start with settling and filtering, then maybe doing softening or reverse osmosis, and then finally doing irradiation or chlorination. So that's kind of the basis of water treatment. As I said, a multi-step process. So I have another video here that talks about how Singapore, I don't know if you know where Singapore is. It's a nation state in Asia. It's just on the tip, just next to Malaysia. They are a very small country. They don't have a lot of resources, natural resources, because they're very small and it's very much a city. But they are very focused on having water for their population. So you'll see what they do is they collect all the water they can. They get rainwater, they get runoff of anything they can, and goes into their system. They also basically they also take wastewater. So the sewage water, they'll take that and they'll reclaim it and they'll reuse it through a series of process steps. And I know it may sound disgusting, but that is a way for them to reuse and basically keep their water balance intact. They also buy water, like from Malaysia next door. They also do desalination. So they take water from the ocean and take the salt out of it, which is very expensive, but it's another water processing step. So what we'll do is we'll show you the video here and you'll see that it's there's a lot of steps that go into it. And it's a nice way to show how you can integrate everything, all these different ways of getting water. So that gives you a feel for kind of, the process steps that can go into a water treatment plant. Now, we had some questions actually that were sent to us earlier that I just wanted to talk to. In Jenkintown High School, they asked, why don't water treatment plants use distillation to clean water? So that's actually a very good question. And you can use distillation. For example, there's if you think about desalination, if you took a bunch of seawater and you were able to enclose it and then heat it, maybe just with the sun, you could get the water vapor to condense. If you could collect that, that would be clean water. That would be water that didn't have so much salt in it, because you've basically distilled the water off. Now, the reason we don't use distillation on a large scale is because it takes a lot of energy. It takes a lot of energy to evaporate water. And that's why all these other systems and all these other process steps are more efficient and lower cost. Somebody asked at Bladensburg High School, some chemical reactions such as combustion and cellular respiration produce water as a byproduct. That's a very, why doesn't this impact the amount of water available? That's a very good point. I know that earlier in the video, they said that water is a closed loop. Basically, we're drinking the same water that the dinosaurs drank millions of years ago. It's not totally true because yes, most water on the vast majority is on a closed loop. It evaporates, it rains, it flows into the ocean and evaporates and kind of goes in a cycle. The only way that's broken is if you actually do a chemical reaction and you can produce water by chemical reaction. Or you can actually use water in a chemical reaction and have a sink of water that way. But that's much smaller. From a practical point of view, when we're trying to make a lot of water for people, all the people and all the uses of water, it's making it using a chemical reaction is not that practical. How efficient, this is from Marion County Knight Academy, Kentucky. How efficient and effective is the water filter we're going to build? While it won't remove everything, would it be sufficient for a life or death situation? I wouldn't rely on it for a life or death situation. As I mentioned before, the water filter you're going to make is going to get rid of the suspended solids. If you have dirty water, you can get rid of the large chunks that are in it, but you don't know what kind of microbes are in it. It's the microbes that are going to be dangerous for you. And then how do you assess the suitability of different water treatment technologies for specific applications? This was Westwood High School in Tennessee. That is to the core, that question is right to the core of engineering. Because engineers, when they design a process for cleaning water, they have to figure out what is my starting water. Because you have to start with some water, and that water, depending on where it comes from, it'll have different types of contaminants. So you don't always know, it's not always one process that works best. So depending on if it's water from underground, then it probably doesn't have any suspended solids, but you might have to soften it or do some other process to get rid of the dissolved solids. If it's water on a surface, like in a lake, it might be very clear, but you might actually have to irradiate it or add some chlorination to kill any potential bacteria. So it really depends on where the water starts, as far as what kind of process steps you need. So let's go to the next. Talk a little bit about the lab you're going to do. So you're going to now be building and designing and optimizing a water filter. What we want you to do is take some very basic. We're gonna make some dirty water for you. Well, you're gonna make the dirty water. You'll start with tap water, and then we're gonna put some suspended solids. We're gonna put two types of suspended solids in. One is just black pepper, kind of coarse black pepper. The other one is actually cinnamon, so it'll smell good. The water will smell nice. But the cinnamon you'll notice, is very, very fine. So it's going to be harder to get that out compared to the black pepper. And again, as an engineer, you're going to have to think about, what do I have in my water? How should I build my filtration and my filters to optimize the use and the removal of these contaminants? So you've probably heard of the engineering design process. I'm not going to go through this in detail. My favorite or my best explanation of engineering design process is that engineers try things, they observe it, and then they improve them. So they're constantly improving their designs, constantly improving what they understand until they get to a design that works for them and works for the situation. So we talk about filtration is what we're really working on. Here's a couple of examples of very creative uses of engineering design to design a filtration systems for water needs. So you can see on the left, they have something called a life straw. You can see that cross section, it looks like activated carbon and maybe some other type of filtration material in there. The idea is that if you're if you are out in nature and there's a stream nearby, at least, or some lake or water, you could use this to try to clean the water before you drink it. Now, again, I don't know how this is designed. I don't know exactly if this also removes bacteria and other living organisms, but that's the idea. It's kind of an emergency water source, water treatment source. On the right, you can see the ceramic water filters. I think this is one where they're using the nature of ceramic that's partially porous in order to filter out the water very slowly, so it comes through the pores of the ceramics and actually filters itself. I don't know if you've ever seen a Brita pot or a Brita filtration system where you put water in the top and slowly the water goes through a filter, and then on the bottom, what's on the bottom is a little bit cleaner than what went into the top. So water filtration, what is it? It's basically the removing or reducing the concentration of particles, including suspended particles, parasites, or other undesirable contaminants. What industries use the process of water filtration? I mean, there's any industry that needs clean water is likely to have a filtration step in their water treatment. What fields of engineering would be involved in the process of filtration? Well, environmental engineering, civil engineering, chemical engineering, mechanical, because you're trying to do this on a large. If you're trying to do it on a large scale, you have to design large structures. You have to have filtration media. So there's all kinds of different expertise and skills that are needed to design a filtration system. There's something called multimedia filtration, which is media is basically what's in the filter. That's what is kind of trapping the contaminants. And if you can imagine from the name multimedia, that means that there's more than one type of media. So quite often you'll have a coarse layer of pebbles, maybe at the top, something that's slightly smaller pebbles below that, and something very fine at the bottom. So that you're first capturing the large particles, but not clogging up the filter. And then next you're getting some slightly smaller particles, and then you're finally capturing the finest particles. This is what you're going to be building today. You're going to have a couple of different types of media that you can use, and we're going to want to see how effective you can design a filtration system, a multimedia filtration system. So I think this kind of summarizes what you're seeing. Excuse me for a second while I get something from my throat here. We've provided you with some gravel, some sand. There's cotton balls, coffee filter, the napkins, paper towels, some things you might be able to find in your classroom. What you're going to do is you're going to build a little water filter by taking the plastic bottle, excuse me, cutting it in half. The bottom part is going to be where you collect your clean water, and the filter will be in the upper half. And it's up to you to decide what kind of filtration media you use, what order you put them in. And the goal is actually twofold. I'll show you in just a second. You want to make the water cleaner than it was when it started, but you also want to make sure it flows pretty well, because there's no point in making super clean water if you just get a couple of drops coming out the bottom. So this is a classic case of trade-offs. How do you decide how you can get enough flow, but also clean water? So here's again is some of the stuff you're going to have. As I mentioned, you're going to use your pepper and your cinnamon to make your dirty water. And I want you to make sure that you keep some of that original water so you can compare it. And then you're going to use these other materials to be media for your filter. Couple of hints. Don't use all your materials at once. Try to make it so that you can do a couple of iterations. Before you build anything, think about how the water is going to flow. So if you have coarse material on the top, the pores are going to be bigger. Fine material on the bottom, the pores are going to be smaller. So you don't want the materials or the filter to clog up. right at the start, and then nothing comes down below it. So just think about logically, how your contaminants are going to be captured. Before you actually run your filter, you should pour just purely clean water through it, just to make sure it's all settles, it's kind of condensed, and everything is right. So that, everything is at a good starting point. And then throw away that clean water and then start testing your filter. And as I said, try to plan to do a couple of filters so that you can see the impact of how much material you use, and also the order in which you use it. So here's a little video just to give you a little bit of inspiration on what this could look like. So you could see at the end there, you had the starting water, which was murky. You had the filtered water, which was less murky. Still not perfect, but better than the original water. Now, the question is, how do you measure the murkiness of your water? And this is actually called turbidity. If you say, how turbid is my water? That's a measure of, or it's a description of how much stuff is still floating in your water. So there's a scale. And this can be measured, it used to be when we would do these labs live, we had a machine that actually measured turbidity, and it shot a little light beam through the water, and then it would give you a number. But we don't have that, so you have to use just this rough scale. So the scale of turbidity is called NTU. And you might ask, what is NTU? And even though I've been working for more than 30 years and I used to work in the water industry, I still have to look up how to pronounce this. So NTU stands for nephelometric turbidity unit, but just don't worry about that. Just call it NTU. So a high NTU has a lot of stuff, not dissolved, but floating in it. A low NTU has very, very little stuff floating in it. And we want you to try to measure your NTU levels before and after in your scale. So anyway, the last part of the exercise here is to look at the economics. Now, engineering is all about solving problems, but they also have to be economic solutions that work. So what we want you to think about is how effective was your filter? So I think what we have is I don't know if maybe we don't. I think it's in the workbook. We have the cost of the various elements of your filter. So you have to add those in. And then depending on the turbidity you achieve, you'll have a penalty cost, if you will. So if you have very clean water coming out, say here over at the filtered water is really, really clear, your penalty is only $10. If you have not so clean water coming out, you didn't remove many of the particulates, it's going to be $70 or $100. So again, you want this to be cost effective. And the reason there's a penalty cost is because typically your filtration will be multi-steps. So if you can filter everything in one step, that's cheaper than having 10 steps. And it might take 10 steps to get the water turbidity down to where it needs to be. So that's the basis of it. So that's the breakout. And I don't know if I'm over time or not, but I think now you guys should be able to get started on this. And let me hand it back to Monica on what the next steps are.
Well, thank you so much, Eric. And we are going. Welcome back. It is time for our Q&A for our water treatment day. Today we have the amazing college mentors, Sinai and Lindsay. They're going to introduce themselves, but this is your opportunity to ask them any questions. So please feel free to type your questions in chat. The ET staff is here monitoring the chat, so we'll pop in if we see any questions come in. Don't be shy, but I'm going to stop speaking and let the two stars of this session take it away. Lindsay and Sinai, your show. Oh, Lindsay, you're on mute.
Hello,
There you
everyone.
go.
Uh, um, Let me share screen real quick, and we'll just get started. So let's just go in. Once. Okay. So give me 1 second.
Let's have Lindsay share, since it seems like your connection is a little bit spotty there. Lindsay, you want to take over that sharing?
Yeah, I'll go ahead and try.
Thanks. There we go. Thanks for hopping in there, Lindsay. All right, but Sinai, you're up. Your slide is first.
Yeah, sorry for the technical difficulties. Hello everyone, my name is Sine Bus. I am a current senior at Cornell University studying environmental engineering, and some of my interests in engineering are in the biomed and biotech industry, which is kind of different to what I'm studying, but I'm also interested in sustainable development and renewable energy. So those are some topics that I've been interested in. And in terms of my involvement with ET, I started being an intern last summer, helped with some of their curriculum, and I was a data developer, and I helped with the wastewater and agriculture labs as well. Next slide, please. And what am I up to? So looking at my trajectory since high school, which I feel like was not looking at the years, it kind of was. I was involved heavily in a lot of STEM programs, and one of them was Summer Math and Science Honors Academy at UC Berkeley. There, I worked with a lot of other peers with same backgrounds as me, so underrepresented. And we built our engineering skills, learned a lot of CS, engineering, system building. So definitely a lot of skill building and growth. And later on in the beginning at Cornell, I started getting more involved with a project team here called Agua Clara, which their main mission is to provide sustainable water resources for communities in need in Honduras. And I thought that was amazing thing as an environmental engineer. I was like, let's just get started with the water treatment. So definitely will be connected to this lab, but later on, I started interning at other companies. I decided to start into the biotech industry. So I worked at a company called Avail, which we were focused on bridging gaps during medical procedures. And I thought it was very interesting. I was a manufacturing intern, so did a lot of hands-on work. And I really liked it. So hopefully go into my master's in that field, or again, work in the biomedical field. And next slide, please. And then in terms of visual trajectory, I think if you click one more time, I think there's an arrow missing somewhere. But basically, first started building my skills, working with a lot of people, working in different projects. So the one on the top right in that little section on the left, we were working on renewable energy systems. So that's a little example. And then started interning at DoorDash, Zymergen, and then Avail. So a lot of companies. And the pictures on the right top, those are I'm working on the project team I am part of at school. So you can see a little hands-on, looks kind of intense, but we were just manufacturing a lot of things. And obviously there was some lab work, some data analysis. So that's later on when we built the system we wanted to. And then on the bottom left corner, that's our main product at a veil being used during surgical procedures. So we were able to see first view of how it would look. And yeah, that's just an insight of my trajectory and how it looked visually. But next slide and on to Lindsay.
Hi everyone. My name's Lindsay Roney. I am a junior at the University of Notre Dame, and I have been involved with ET most of this year. I was an intern this past summer, and I helped work on their app development, cybersecurity, their water treatment, and some other curriculum-based things. So my interests in engineering, I am a computer science major. I also have a minor in the digital marketing, which is in the business school. So kind of random, but also has to do with technology. But other than that, I am really interested in cybersecurity. That's what I'm hoping to do as a career. And then I'm also interested in mobile app development, more of the user interface sort of thing. So kind of design, all that jazz. And then I am also interested in data privacy. Um, to go over a bit of high school, that's where you guys are right now. So my high school, I was lucky enough that we were required to take computer science courses in order to graduate, and I just liked the one that we had to take. We were required to take, so I decided to take the AP ones after that. And in high school, we also had a computer science honor society, so as a part of that, and with that, I was able to tutor with Java and get involved and help with the required class. And then all throughout high school, I wasn't entirely sure what I wanted to do, but I thought I wanted to do engineering because I really like being creative and I enjoyed science and all that sort of stuff, but I was still a little bit unsure of what discipline. And other just random things. I was involved in NHS, Spanish Honor Society, Key Club, Ambassador, soccer track, all that sort of random extracurriculars. So when I applied to college, I applied as a computer science major, but then over the summer, I decided to change to mechanical. And then throughout my freshman year, I changed back to civil, then back to computer science. So if you guys have any questions about changing your major in college, I am the perfect person to ask because I did that so many different times. But it was my first computer science class in college that inspired me to stay with computer science as I had originally planned. It took me a little bit to get there, but I'm really glad of where I am. And in college now, I have a scholars program with data science, and I also have a concentration in cybersecurity. So it's basically just my elective classes are cybersecurity focused. And I also do research on with large language models in order to reduce the security risks and all that sort of thing. And a little side things, student international business. I was on a Microsoft project, so we got to go to their headquarters, present a project there in Seattle, which was super cool. I'm also really involved with the Society of Women Engineers and the Department of Campus Technology here at Notre Dame, where I'm going to help write a paper on how Notre Dame is going to kind of approach all of this artificial intelligence things regarding rules and that stuff. And I also have an on-campus job with my computer science department. So here's just a kind of a pictures of what I'm up to. Here is on the top left is a picture of me and my team at Microsoft headquarters in Seattle, as I was talking about. And there's also a picture of the leaders of the Society of Women Engineers and me at a game day. Notre Dame is a huge football team, or yeah, huge football school. Love it there. And just a little bit of an insight into my research as well on the bottom left. I do mostly using regex expressions, which is basically just matching different sentences and all that sort of thing. So yeah, so if we want to move, Monica, take it over again.
Yeah, this is your opportunity to ask our mentors any questions, but I know that there were some questions submitted via the form by your teachers from our school. So I'm going to start off with one of them, which was from Mercy Academy in Kentucky, that asked, what should we do in high school to prepare for a career in engineering? And they specifically said civil, but they said any kind of engineering. So if you guys want to give them some advice on what they should be doing now in high school. And while they're answering that question, teachers that are in our Zoom, type in the chat, do your students have any questions right now for our mentors? So go ahead, Lindsay and Sinai, take it away. What should they be doing in high school right now?
I can answer this question just because I forgot to mention, I was double major in civil and environmental. So I did trickle into the civil engineering aspect of careers. But I think in high school, even if you are not set in civil or whatever engineering you want to do, I think it would be very helpful to just get involved in terms of maybe an internship. But I know internships, especially in high school, can be really tough to find. So I would suggest even like volunteer experiences. So I know a lot of, I've met a lot of companies that have labs and they take volunteer students. And especially if you're in high school and you just reach out to anyone on LinkedIn or anyone in your network and you're like, hi, I'm in high school. I am interested in this and that. Like, I would love for an opportunity to even shadow you. Like, if you just wanted to shadow someone and build your network, I think that would be very helpful. And you're a high school student. They're not gonna think like evil intentions out of it. I think they very much appreciate it because they can see like younger students being very involved and very passionate about what they want to do. So I would say definitely fill in your summer. I think that's the time where you can explore a lot and do a lot. So um, I definitely did a lot of extracurriculars during the summer. I think that helped me a lot to build my engineering skills and to figure out what I wanted to do. So definitely just use your summer for good and use your time wisely and just reach out, find resources. I know there should be a lot.
Yeah, I agree with everything Sinai just said. I did not get very many opportunities engineering wise in high school. So I think applying to colleges, I was just through my essays and all that sort of stuff, able to show them my passion that way. I was involved with, as I said, a couple things computer science wise, but my school wasn't huge on engineering, that sort of thing. We didn't have any clubs or focus in that sort of way. But I think just the best way is to write your essays, show that you're passionate about it, that sort of thing. Um, we have another question about the cybersecurity path. So, do I recommend going in as a computer science major? Is there a better path? So, this question is definitely more school specific. I can really only talk about, I think, my experience at Notre Dame and maybe at what I know in general. So, here at least, the computer science path is definitely the best path, I would think, just because within the College of Engineering they have concentrations for cybersecurity, that sort of thing. But there's also computer science in the College of Arts and Letters, and I also know that there's a bunch of online certificates and stuff. So technically, you don't even have to go to a 4-year college, I believe, to have a career in cybersecurity. You can go and do boot camps online, that sort of thing. There's a bunch of different paths. Just choose what's best for you. There's as I've been applying to internships for my this coming summer, I've realized that you can also major in things such as information technology. They like math majors as well. Usually anything tech focused is helpful. As in what schools I would recommend for cybersecurity focus. Again, um, I would just say I think that really depends on how you want to do it. If you want to do the certificate route, the boot camp, or if you actually want to go to college and get a 4-year degree, that sort of thing. But there are a bunch of different paths. I wish I had more knowledge on just cybersecurity schools in general, but I think a lot of schools have a bunch of different ways you can do it as well.
So
So
I'm sorry to hop in, guys. We have a school that has to wrap up for the day, and they want to share what they've completed because they're very proud of their work. So I'm gonna stop the Q&A for a hot second and let Martin Van Buren. Can you share what you guys have done, and then we'll get right back to the Q&A because I know you guys have to leave.
Go ahead. Hi, my name is James. I'm from Martin Van Buren. We made a coffee filter. We took 2 coffee filters, put it to a water bottle, and tied it with rubber bands. Now, my friend Tristan would like to explain the rest.
So basically, filter to filter out the cinnamon from the water, and when you pour it through the coffee filters, you filter it and it drops to the bottom of the clean water.
That is awesome. I think that water is very clear. I see Milton hopped in the chat with that. Thank you so much for sharing, Martin Van Buren. We appreciate that. And please just thank you for being here for part of the day. And sorry to interrupt. Sinai was about to speak before I interrupted, but thank you for that. Go ahead, Sinai. You can keep going.
I think I was done. I think Lindsay was finishing up what she was saying.
yeah, you can go ahead and answer the next question.
Okay, sounds good. So I want to answer the one about how do you balance school activities and social life. I think specifically in terms of like how much you get involved, I think it's very important to obviously not overbear yourself. I think I was definitely in that spot, especially senior year when you're applying to schools, you're trying to do still extracurriculars, you're trying to, if you have to work or still trying to, have friends, have a social life. I definitely believe as a if you're an overachiever, even if you're not, I think it's natural for everyone to kind of want to do everything, but it is also very, very important to kind of gauge the limits of what you can get involved in, because in college you're going to have that too. You're going to have so many other responsibilities, and at some point you're just going to have to be like, okay, I can't do this like specifically, or I can't fulfill this role. So I definitely agree that there should be a balance, and I definitely, when I was in high school, would kind of prioritize what I thought was most important to me. So, for example, I was part of dance a lot. So I was like, that helps me a lot with my mental health. That keeps me sane. So I definitely want to prioritize that second after my, let's say, like after my academics. And then I would say, okay, like maybe social life some days is better, or it is more of a priority than other days. So definitely just keeping organized, I thought helped me a lot, and just planning ahead, because I think definitely things are going to happen during high school and you're going to have like, I don't know, maybe a day where you can't do social life or you can't do activities. So definitely planning ahead and prioritizing, making that list, and just reflecting a little bit, sitting down and being like, okay, what do I want to prioritize today? Because it can get overwhelming, but I think just planning ahead again, I think would help a lot.
Yeah, just kind of going off of that, I think the transition from high school to college was difficult for me freshman year. It was definitely balance was something I learned throughout the transition. And I think one thing that really helped me is realizing where I'm able to focus. For example, I have 3 roommates. I live in a quad here on campus. So I know that if I have an exam the next morning, I need to kind of remove myself from the room. I can't study in there, not going to focus. But I'm not shutting myself out completely from them, like not hiding away to do my homework. I also make a point to kind of fit in homework gaps when I can throughout the day. I'm not a big person on sitting down from like 8 to 11 p.m. and doing all my homework. I like doing it during breaks, or maybe I'm fortunate enough to be able to do some homework at where I work, that sort of thing. I think breaking them up really helps with time management and balance as well, because you're not stressing yourself out by constantly staring at the same homework problem or assignment, that sort of thing. You can come back to it, maybe switch homework assignments. And I think extracurricular wise, balancing those is definitely having a calendar, realizing what you have time for, and planning around that. If you can get maybe to your meeting 30 minutes earlier, do homework then, and then maybe stay in the same building, do 30 more minutes of homework, and then go home, that sort of thing. Social life is definitely really important. I also really recommend prioritizing sleep as well. I'm sure you all heard that, but I try to cut myself off by I think 11 p.m. every day. So nothing insane. I am able to manage while having a social life and plenty of extracurriculars. So I'm sure you will find a balance if you decide to go wherever you go into college wise. Um, in regards to which college majors align with water treatment, I would say definitely environmental engineering, civil engineering, even mechanical engineering in some ways. Not really computer science unless you're talking about the technological aspect of that sort of thing. I don't know if Sinai, if you want to add on to that.
Yeah, I definitely agree with what you said. I think um, also if you're looking into like colleges you want to go into, like for example, Cornell, if you were to do environmental, we're very water heavy. So also I would look into like what college emphasizes in what, or if they have different concentrations. But yeah, so mainly here it's environmental, maybe biological engineering, because they look into like the actual treatment processes, and mechanical as well. But definitely just doing a little bit of research into like what aspects each college has.
So I have a question that We're here with all these high school students, and I'm sure some of them are thinking about what's the next step? How do we get into that college for that cybersecurity class or for those civil engineering and that environmental class? Can you talk to them about what that college process was like, your application process, and any recommendations on how you selected your college?
Yeah, I can start with that. So I'm sure you guys all remember COVID. My class, so I was a junior when all that one happened, meaning that I wasn't able to take the SAT or the ACT. So I think all of the colleges I applied to were test optional. I think the college now in that regard, it really depends if they're still test optional. I think Notre Dame is test optional for the next 2 years, I believe. Don't quote me on that, but so I didn't really have to worry about that, but I think so test optional, you were able to still submit everything else. They kind of just didn't think about that score. So I like to believe that my main strengths were probably just my essays. A lot of colleges like to talk about how they like to look at you holistically. It's not everything about your grades. It's not this person has a 3.9, so they're automatically going to go get in. They want to see that you have like passion about what you're going to study about the school. And even if you're not sure, I think talking about something that you are passionate about and maybe how you're going to address figuring out what you're going to study, that sort of thing. There's plenty of people who go into college officially undecided as their major, and that's completely fine. I think a lot in my essays, I talked about, I think essays are probably the like kind of the scariest thing, but talking about like life experiences, I think my Common App essay was about my dog and how I got her on Christmas, that sort of thing. It doesn't have to be a super deep philosophical realization or like you curing cancer, that sort of thing. They just kind of want to know who you are as a person. So don't stress too much. I also being hate to keep talking about COVID, I wasn't able to visit any of the schools I applied to. I chose Notre Dame without ever seeing it. I saw it for the first time the summer. I was able to go the summer before I started, but I obviously, as I just said, didn't see it before. So a lot of colleges have very good virtual tours, and I was blessed enough to talk to some kids from my high school who were going to Notre Dame or had gone. So I think talking to people and kind of getting vibes, even Googling YouTube videos of room tours. I know I did that a lot as uh upcoming freshman. So there's a lot of information online. You just got to reach out to people, kind of look for it. You're not on your own. There's a lot of people out there willing to help. As you can see, I'm rambling on about my college experience. That's mostly what you're going to find about people who are really happy to share information.
Yeah, I think to bounce off of that, COVID was definitely something that affected me a lot. I think I'm a year older, so freshman year, that's when I got into or that's the first year I went into Cornell, and the college experience was different, so it didn't affect me as much as the application process. But I definitely think some advice would be just start early. I think it can get very, very stressful very quickly if you start late. If you have essays, like with them, reach out to people, reach out to or not professors, teachers that want to help. I know there's so many that are willing to help you, and definitely, yeah, like how Lindsay had said, like show who you are as a person. I definitely didn't have the highest SAT score in my whole school, so I think obviously grades aren't the whole like said and done. I think especially extracurriculars showing that you're a well-rounded person, that you just don't just do academics, that and it doesn't even have to be extracurriculars in school. It could be like working for financial reasons, or working for necessity, or working because you want those skills, or even volunteering, or family, like if you take care of your siblings, like that is, it shows a lot of who you are. And that just shows like, yeah, I have responsibilities outside of school and I'm still doing good in school. And definitely just advocating for that and vocalizing that a lot. Do not be shy about vocalizing like who you are, how proud you are of yourself. Like there will be people in these college applications that will be like, I am the best person in the school. I am the best applicant. You should not shy away with your confidence, because they definitely want to hear it. They don't know you, so they definitely want to see who you are. And that's something I definitely had to learn throughout the application process, because I was like shy and I was like, I don't want to talk about myself. I don't like this. So definitely just hone in that just for at least these college applications. But yeah, definitely starting early and hone in on who you are outside and inside of during.
All right, I'm going to hop in here because I see a question in the chat. I'm not sure if Lindsay and Sinai can speak to this, but I know there are some ET staff engineers on the line. Maybe they can hop in. There's a question from George Washington Carver High School, and it says, is getting a doctorate degree worth it in engineering? Just some thoughts on that. Do we think it's worth it? Oh, I see Betsy came off mute real quick. Hey, Betsy.
Yeah. So I did not have a doctorate. I did not even have a master's when I started working at NASA. So I think it's really going to be dependent on the area that you choose, whether or not having additional schooling is helpful in that area. You could definitely do some amazing engineering jobs without even a master's. So don't feel like you are committing to like 7 years of like your life. You know, you can go ahead and do 4 years and go and have a great job, and then find out that later on maybe you want to get a master's in that kind of engineering. Maybe you want a master's like an MBA where you can help guide the programs that you're working on and things like that. So it's all kind of dependent on your areas that you're focused on. So don't feel like you're totally committed in having to go up to a master's or even a doctorate level.
Thanks so much for hopping in there, Betsy. Appreciate that. If anybody else wants to hop in on that one, you can. But there's another question. I'm not sure. Again, this is for anybody who has any information on this. Somebody from Challenge Prep Academy is asking, they want to do game design one day. What college major aligns with game design? And anybody have any insight on game design? And you can say, no, that's a very specific question. Let's see. Go ahead, Sinai.
No, I was just gonna say quickly, I think definitely, at least for us, there's even game design classes here at Cornell, and it's all mainly like CS people, or like intro to web design people. So definitely not my realm, but just wanted to put that out there. It's definitely more CS related, like yeah.
Yeah, I was gonna say the same thing. I think most of the people who go into game design are studying computer science, and they kind of take the classes relating to that, like different game design classes, or maybe they join clubs that do something similar, that sort of thing. I'm sure there are schools out there who have specific majors for game design, but I feel like even just doing computer science is a really good start to build the foundations that you're gonna need to go into that.
Yeah. Yeah. Sanai and Lindsay have excellent answers as always. Also, a little bit of art sometimes is kind of nice, like 3D art creation, 2D graphics, 3D graphics, little spatial intelligence, user interface. Those are also, really, really great skills. Yeah, animation, yeah, as Bessie put in the chat. I can't wait to see the games you all design. I'm excited. I'm a gamer. So
Well,
I'm ready for this. Let's do it. Let's do it, engineer tomorrow. We need a game design. We need a
uh,
game design curriculum.
here
That's
we
what
go.
we need.
New curriculum at ET from our first lab event day. Awesome. I love
Yeah.
it. So we have 2 minutes left. I'm going to put Lindsay and Sinai on the spot. If you could give these high school students one piece of advice today for, for moving forward down this path that they're on, what advice would you give them? Final thoughts for our students today.
I would say just kind of trust in the process, kind of cliche, but I think you truly will end up where you're gonna be. I had no idea where I was gonna be senior of high school. I didn't choose my college until I think the deadline's like May 1st. I think I committed April 31st or April 30th, whatever is the last day of April. Um, so it is really scary in high school if you're thinking about college now, that you don't know where you're gonna end up, even where you're going to live in a year or two, but everything's going to work out for the best no matter what course you or path you take, major you do. You'll figure things out. You'll get on the right track. As I said, I changed a bunch of times and I'm really happy with my major. I love my classes, my professors, all that sort of thing.
All right, Sinai, you're up.
Yeah, to bounce off of that, I definitely agree, like trust on the path. And I think something I struggled with during college was feeling like I belong. So going off of that, like definitely do not think you don't belong there. And there's a difference between like, oh, maybe you don't want to do engineering down the track, but like if you really like engineering, you want to do it and you feel like you just don't belong or you feel like you're, let's say like you're behind, don't do not stop. Like keep going. Do not be afraid to ask for help. So many colleges have so many resources. I was like the type to be stubborn and be like, I can do this by myself. I'm independent. I don't need anyone's help. And quickly I realized I was like, that is not the way to do college or do life in general. So do not be afraid to ask for help. Go to office hours, study with people that are like the same, that are experiencing the same thing. Just reach out. Build your network with your peers, with your professors, with your mentors, whatever. College is for you and it is there for you. So take advantage of it as much as you can because it's only like 4 years or 6 years, how many long it is. It is not forever. And I've heard so many people, and I would even say like it is the most monumental like years of my like my experience, my career, I want to say. So definitely take full advantage of it. There's so many resources out there for you guys, but yeah.
Great advice from Lindsay and Sinai. It is officially time to wrap up our Q&A session. So I want to say thank you to Lindsay. Thank you to Sinai. Thank you for all the engagement in the chat. Amazing questions. Everybody did a phenomenal job. Recording. Welcome back to the main room, everybody. First, I want to say thank you to everybody who participated in the breakout rooms. We are looking forward to what's happening next, where it's your time to shine, students. We want to see what you created, what you did. Please turn on your cameras. We want to see your classrooms. We want to see your work. So Eric is going to start off just with a little background, but it really is your show. So if you guys want to raise your hands, I will pin you to our screen so we can see what's happening in those classrooms. You can type in chat if your group is ready to roll to present what they've created. And let's get this wrap up underway. Go ahead, Eric.
All right, thanks, Monica. Yeah, so first of all, I looked at a lot of your questions and your comments from earlier in the day here, and there were some great questions. And I think you got a lot of them answered through some of the other engineers too. So thanks for the engagement, and I hope you've enjoyed and had a chance to do a couple of iterations on your filters. And as Monica was saying, this is, for the next, we have it a half hour, or as long as no more than a half hour, but we have our speaker ready in case you guys don't want to show us anything, but I'm sure that you'd like to show us some stuff. So I'd like to see if you guys can show us what your filters, how they performed, particularly the before and after water, if you can show us that. And also want to hear just more about how you designed, what your design was, as far as how you chose what materials to use in your multimedia filter, and how it went. Was there something that was difficult? Was there something that didn't work out quite right? Let's hear from you. So anybody want to start?
Also, Eric, let's see who was able to make the most affordable filter, because I have a feeling we might get some high price filters coming into this wrap up.
That's right. Exactly. Yeah, it doesn't help if you make one drop of perfectly pure water, but that's all you make, because we need more than a drop to quench our thirst. So anybody want to share?
Don't be shy. Let's see what you guys created today. Anybody have anything they want to share? Feel like I don't want to call, but I don't want to volunteer. Tell people to. Let's see. Challenge Prep, you gave a thumbs up. Challenge Prep has a lot of different screens on, so I need to know which Challenge Prep is ready to roll. If you could raise your hand on your Zoom or turn on your camera and show us, I will spotlight you and you guys can unmute and share. Oh, St. Raymond says they have camera problems. Oh, I see a lot of movement and a lot of cameras in Challenge Prep.
Oh, yeah, Challenge Prep's got a lot of things going on. Okay, that's great.
I see one. Let me spotlight this. There we go. Can you guys unmute so we can hear about what you guys did today? We can hear you.
Yeah.
So we start here.
Okay.
Like this.
That's the dirty. It's already settled. You can see some of that has already settled the water, but that's fine.
It's starting to settle.
Yeah, if you stir it up, you'll see the full.
It was like this before.
Yeah, yeah. Yeah, no, good. That's yeah, nice and dirty water. Good.
And the final result was this.
Ah, very good. Yeah, you can see that's gotten a lock there. Still a little bit
I can't do them.
yellow.
Hold on. What?
But that's because it's so hard to get that cinnamon out. The cinnamon is so fine, it's really hard to filter it out. But that looks good. So what did you have in your filter?
So on the top there were cotton balls, and then under the cotton balls was one napkin, and then under
Okay.
that napkin was the sand. Then under
Okay.
the sand were the rocks, and then
Okay.
after the rocks there was the coffee filters.
Okay. To hold
then
it all
that was
together so it doesn't go through.
Yes.
Very good. Very good. And it seemed to work well. Did it clog up, or did it flow pretty good?
I think it flowed pretty good. The sand did drip a lot. It like dripped past the rocks and stuff, and it got into the water a bit.
Right. Okay. 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 Now that I can understand. That's one of the things, these filters, once you use them for a while, they'll clog up or they'll start to flow slower because you're capturing all this stuff. So then, like in a normal industrial scale, you have to stop it and then you backwash it. It's called backwashing. You flow water back the other way to clean out what you've collected, and then you start over. But that looks good. That was a good improvement in NTUs in your turbidity. So well done. Good job.
Thank you.
Thank you so much, Sandra. Do you guys, what did your filter cost? Did you calculate your cost or no?
Did you do a cost?
10 to 40.
What?
How much?
Like the water. How was it?
Are you talking about the turbidity or something else?
The actual the economics. That basically there was, I don't know if you had the time to do, you do the turbidity and then you also add the cost of your filter, and you can get an overall cost, but not everybody gets that far. So that's fine. I mean, Monica keeps reminding me, we got to get to the economics. We got to get to the cost. So
all right.
That's no problem. No problem.
Thank
Good
you so
job.
much. I see another sample from Challenge Prep. I'm going to change the spotlight to this group. Can this group unmute so we can see how you guys did?
Hi.
Hi.
All right, so hello.
Yeah.
Hello. So first I watered like this.
That's the
and
dirty.
it turned
That's the
out-
dirty water. That was the dirty water.
Yes, sir.
Okay. Yeah.
And it turned out like this.
Oh, again, quite good. You didn't have no big particles
Can you
in
repeat
there.
that, please?
You did a good job. That's all he said. He said you did a good job.
Thank you so much.
Do you have
So
your
what-
actual filter?
Yes, actually.
yes.
It's right here.
Let's see it.
Hold on, it's just. So we use this right here. Yeah.
So what materials? Can you describe what you used in the filter?
Okay, so we used cotton balls. We used the sand, and we used the rocks.
Okay. Okay.
And then we put the coffee filter actually inside of the hole where we cut, instead of outside. And then the water was able to come through perfectly still. At first we used a little too much. So I took out some rocks and some cotton balls, and we tried it again. It came out more clear and better than usual the first try.
And I also added onto it.
Yes.
I add a little bit of sand and some more pebbles.
Okay.
I poured it in, and they actually work.
Okay. No, that's great. So that's good. So you did a couple of trials. So you tried a couple of different designs.
Yes,
Yes,
sir.
sir.
To improve them. Very good. Excellent. Did you have a chance to try the economics and calculate your filter cost? Or
Yes, sir. It was about the same as our other classmates as well.
Okay, that's fine. Okay. Okay. Very good. No,
Thank
excellent. And you both noticed that if you start with the dirty water and you let it sit, it actually starts to clean up a little bit on its own, because that pepper is heavy and it slowly settles down to the bottom. So you got almost that's like another step of the water treatment process. By the way, if you're interested, there is an extension to the lab that actually allows you to build a settling tank, if you will, that you can also do even more on. So, but no, good job, nicely done. You definitely had an improvement in your water turbidity there. So
Thank you so much.
Thank you.
Thank you.
All right, I have a request from a school that wants to share, but their camera is not on, so I cannot spotlight them. Oh, they got shy. No, we're not shy here. We're all sharing. Don't be shy.
It's okay.
All right.
There's no wrong answer with engineering, because it's just a question of continuing to learn, and you figure out what didn't work. And in engineering, there's always times where things didn't work, and you just figure it out. So there's no wrong answer. So sharing what you did is never going to be a problem.
All right, until we have another one that comes up. I don't know if you want to get to some more questions or if you have some slides while we wait for some brave souls to come and share with us.
Usually we have more people who want to show their stuff, but anyway, we can go to a few more questions. So let me get to some of the other questions that were submitted early. One was about water treatment plants, and actually Natalie may be able to help me on some of these if I can't figure them out. What chemical or physical properties do water treatment operators monitor daily? And how do regulations apply when a plant exceeds its wastewater processing capacity or treats water for environmental return versus drinking water? That was a question from Hallsville High School in Texas. So I've never been in a control room of a water plant that I can remember. But I know that they're focused very much on water quality. There'll be online monitors to make sure that the water is meeting specifications, and they're also very focused on throughput. So remember, I was saying how if in these filters they'll eventually clog up, and they're basically eventually you'll get a buildup of silt and stuff in them, and the pressure drop is too high. I think one of the things that operators have to keep an eye on is to see when that happens and figure out, they'll divert the water to another filter while they backwash certain filters. So that's one of the things that's kind of a constant issue that they have to manage in a water treatment plant. And then you also mentioned how do regulations apply? So drinking water has to satisfy certain regulations. There are federal rules and regulations of what quality and purity there has to be. So that is kind of the boundary of what a water plant has to work towards. And essentially that is how the water plant is designed. Depending on what your source water is, you have to design the plant so you can meet those regulatory requirements. And those requirements are for the health and safety of the population. Now, I know you may have heard about, there are places where there's been exceedances, like in lead or other types of contaminants or metals in water, and it's that is something that needs to be constantly monitored so that it doesn't occur. I forget what is the name of the area, the town. There was a town in Michigan, I know that had a very bad situation with
Flint, Michigan.
Flint, Michigan, yeah, where they had made a change to the process. My understanding is that they made a change to the water treatment process with the idea of that it would be more cost effective, but it had a negative effect on the quality of the water. So engineers need to understand what those cause and effects are and make sure that they're first satisfying the regulatory requirements for purity. So another question was, what key factors and challenges are considered when creating a sustainable water treatment system for a fast-growing urban area, considering population growth, climate change, and emerging contaminants? That was from Cypress Bay High School, asked that. Actually, I don't know, maybe Natalie, do you want to jump in on that? Because I know we haven't introduced you yet, but I'll introduce you after we finish this, and I think you might be able to comment on that a little bit better than me.
Yeah, that's a great question. But from Cypress Bay, there's a lot of considerations that designers take into place when designing and building a water system. The population growth is certainly one of them that they really need to look into the future and project how this system might grow and what additional homes or what additional industry might be tapping into this system. So a lot of systems are over designed initially for that population growth. And then now when it comes to climate change, a lot of newer systems or systems that are getting improvements are looking at the impacts of weather patterns. They're looking at the impacts of drought, of temperature, of rainfall, and really getting an understanding of how that plays into that specific region, and then sizing the system for those potential climate change impacts. So a lot of that, it's a really great insight, a great question, because there are, a lot of things that go into designing the system, and it's a lot of futures thinking, thinking about looking at the past and seeing what happened in the past, but then also really looking at climate models and looking at the data that we have to project out into the future.
Yeah, that's and I'm sure that that's even getting harder and harder because of climate change, because it does seem that the storms are getting more and more severe. I know that what happens when you have severe flooding, it causes all kinds of havoc to the ability to clean water, to provide clean water to the municipalities. So not only like Natalie was saying, they predict or they model population growth and growth probably of industry, I would assume, right? Because if they're using water, but the added uncertainty of climate change, I'm sure, is adding more factors that have to be taken into account. Is anybody else wanting to turn their camera on and show us what you've done?
I don't have any groups ready to hop on camera yet, but we do have a question from St. Raymond High School for boys, and they ask, is it feasible to desalinate seawater into fresh water, or is it just too costly?
That's another great question. So the way desalination works, there's kind of two major ways. And in fact, there's really one, I think, major way. And then there's an old traditional slow way to do it. I mentioned earlier, kind of the slow way, which is almost like seawater distillation in a way. It's taking water and basically heating it up or letting the sun evaporate the water. And what gets evaporated is essentially distilled water, clean water. It's not salty, but then you have to capture that. So that is how many areas of the world where they don't have a lot of infrastructure, where they don't have a lot of resources, that is a way that they can provide some more clean water for the community. But the actual process of desalinating water is actually quite expensive. It's really energy intensive, because what you have to do is you basically are running it through reverse osmosis systems, as well as other types of filtration systems. And it takes a lot of energy. So quite often a desalination plant will be sitting right next to a power plant, which provides enough energy for the desalination plant to run. It doesn't mean it's not cost effective. It really all depends on what does the community need, how much water is required. Are there no other sources of water? Sometimes that's, I don't know if it's not necessarily called a last resort, but it's one of many ways of providing pure water or clean water for the water system. So again, I think Natalie will be able to maybe talk more about that. But I mean, desalination, I think, is here to stay. It's a question of, can we do it cheaper and more simple, and make it simpler and more effective. But I think it's going to be a technology that's going to be needed going forward as we lose groundwater and other sources of water.
Still no brave souls here, Eric.
Okay,
I'm trying.
Let me go through a few slides, and then we can Natalie can start and talk about, and have our guest speaker talk about her career
Hold on
as
one
an
second.
engineer. Oh,
Miss
we got one?
Nelson, Miss Nelson, we are ready if you are ready. But you have to turn on your camera. I can't spotlight you. You're ready. All right. Let me spotlight you. Thank you. All right.
All right, excellent.
Okay, so we drew a diagram of what we did. And we first put the cotton balls, 3, and then we put the rocks, then the tissue, the
The sand, maybe?
Gravel.
And in the sand.
Okay, okay. So that was okay. 3 count. Well, got it. Do you have a sample of your water?
Yeah, this is the before, and this is the after.
Okay. Okay. Yeah, that looks pretty clear. Yeah, no, definitely very good. So you got a good improvement. Does your filter? Can you see if you look in your filter? Do you see like the particles on the top from the top? If you look at, can you see the pepper and everything in there? Anything in there that it's captured?
Yeah, I see like cinnamon in it.
Some cinnamon too. Okay, excellent, excellent. No, that's good. Very good. Well done. Did you guys try to do the economic cost?
No.
No. Okay. Yeah.
We didn't get to do it.
You didn't get that. Okay, no problem. Good. Did you manage to do multiple trials, or was this one design that you did?
We did 2.
You did 2. How did you change the design? Did you change the design from the first to the second?
Oh yeah.
What did you change? Do you remember?
Oh, we put a less amount of, in the first one we put less cotton balls than the first one, and less coffee filters.
Okay, very good. Great. And do you think it made a difference when you made the different design? Did it make a difference in how clear the water was?
Yeah, the second one looked better when you put more of the coffee filter than the cotton balls.
Right, that makes sense. Yeah, there's probably more little holes and smaller holes as you added more filtration media. So good job. Nicely done.
Thank you so much. And Ms. Nelson, I think that student deserves some extra credit for getting brave and coming and sharing with us. So thank you so much.
I definitely agree. Thank you.
Very good.
Thank you so much, Ms. Nelson. Fantastic job. All right, Eric. Sorry. Go.
Oh, no problem. No problem. Let me.
I'll keep you posted if somebody else is ready to roll, but not yet.
Okay, sounds good. Let me go ahead and share my screen, and we'll just go through a couple of final slides here before Natalie talks about the work that she's doing. So far so good. I mean, you guys have done a nice job, at least what we saw. And hopefully you got a sense of how engineers have to make trade-offs, design. I mean, the trade-off here was how clean is your water versus how fast is it going to flow through your filter. And I'm glad that you guys got a chance to do multiple trials and see the difference as you made a difference to your design. The results changed a little bit. So that's just how it works with engineering. So let me. I know that somebody asked a question about desalination. So I did have a page here that talks about desalination a little bit, and this is the one that I was telling you that if you take salt water and you essentially have it in a contained area where you can expose it to the sun, and then if you can capture the condensate of what gets evaporated, that is desalination, and that's a way of making fresh water. But it's slow. It's a slow method because it takes a lot of energy to do that. If you want to do it more on an industrial scale, you will need to actually design a multi-step process, kind of like if you guys designed one step today, and basically use essentially reverse osmosis, which is how you then are able to separate the dissolved solids, so the salts, and concentrate them in a concentrate stream and then have the other cleaner stream come out as having a lower concentration of salt. And then you may have to do that many times. You may have to put that through multiple steps of reverse osmosis for it to work. So anyway, but that's how desalination works. I mentioned that in Singapore, that is one of the, they have a lot of sources of water, and desalination is one of them. It's a kind of an expensive way to do it, but again, it's sometimes the costs pay off, and it's one of the best options for communities that are near the ocean or have access to salt water. So another thing I just wanted to mention was, I think I mentioned before, aquifers. Essentially, you can drill and get your water from a well. And essentially what you're doing is drilling into an aquifer. But an aquifer you can think of is kind of like just a big holding tank. And what you want to make sure, though, is that you're not just taking water out, because the aquifer does recharge itself through natural process like rain and things like that. But if you continue to withdraw water faster than it's replenishing, the aquifer can change and you can overuse it, and the water table will go down. And there are risks around doing that. I know that I've seen in the news lately that by overusing aquifers, you can actually have settling of land because there's less support of the land. So again, aquifers is the source of groundwater. Water in an aquifer is kind of naturally treated because it came from rain. It kind of went through the ground, and which kind of filtered it. But it also picks up a lot of dissolved solids, and it's usually typically very hard water. But anyway, it's another part of the whole water access that's important. Now, just to give you a little bit of a sense of, if you really enjoy or want to work in the water industry, there's a lot of different ways you can do it. Of course, we're always talking about engineering and the benefits of going to a 4-year college for engineering or university. The things that you can learn as an environmental engineer, or a civil engineer, or hydrologist, and there's a lot of different areas that you can go into through that route. But you can also work in the water industry, without a 4-year degree. You can still become and learn the skills to become a tech, to become an operator. So if water and water treatment industry is interesting to you, there are certainly many paths you can take. Just to get an idea, there's a lot of industry, or there's a lot of organizations that are involved in not only engineering, but water engineering, civil, environmental, and there's also internship opportunities. But so what I want to do, though, let me stop sharing here. I think it would be good to get right to the best part of the day here is to learn a little bit more about how a real professional engineer works in the water industry. And I'm looking forward to hearing more about the Engineers Without Borders organization. So let me introduce Natalie Selmo. She got her degree at University of Pittsburgh as a civil and environmental engineer. And as I said, she works for Engineers Without Borders and has been working. She'll tell you a little bit more about what she's been doing. But this is an organization that provides volunteer engineering that really does infrastructure support around the world. But I think Natalie's focused more in the US for communities that need a little extra help as far as building their infrastructure. And I understand that a lot of the work is around the water industry. So with that, Natalie, let me hand it over to you, and look forward to hear about what you do, and also how you became and why you became an engineer, and the good of the industry, and what fun it is.
Thank you so much, Eric, for that great introduction. It really is just such an honor to be here with everyone today. I'm so inspired by those of you who shared your filters. I'm inspired by those of you who asked such insightful questions. And I just already believe that if you guys are the next generation of engineers, then we are in really, really good hands. As Eric said, my name is Natalie Salmo, and I am joining you all today from Golden, Colorado. I am a senior program engineer at Engineers Without Borders USA, and I have the privilege of sharing my engineering journey with you all. So every engineer has a different journey, everyone has a different background, everyone's motivated by different things and inspired by different things. And I'm hoping that maybe some of my experience will resonate with you all and encourage you to join the engineering field. You also learned a lot today about water access and water treatment. And I'm just really excited to share how my work and my experience as an engineer ties into what you learned today. So let's go ahead and get started with a little bit about my background. Everyone see my screen? Awesome. So let's start back with my childhood. So when I was a child, I was that child that asked about 1,000 questions about everything. I always needed to know, the how and the why, and I would persistently just dig deeper until I, in my little child brain, had an understanding of how things worked or why things were the way they were. I also was one of those kids that actually just liked math class. I loved geometry. I loved the preciseness of the problems. I loved when I solved a problem correctly. And I also grew up around construction. So my dad was a carpenter. He was constantly building things and fixing things around the house. And I really grew up helping him. Or at least I thought I was helping him, by holding boards and getting tools and really just seeing things come together from the ground up. I also thought it was really cool when we would drive around the city of Pittsburgh, which is where I'm from, and my dad would point to certain things and say, I built that. And I would just have such pride in knowing that, my dad was able to see the construction and be part of the construction of certain buildings. So I think it was really that curiosity as a child, my inquisitive nature, combined with my interests and just I liked math, that really was the foundation for me becoming an engineer. When it came time to think about a career path and picking a college, I landed at the University of Pittsburgh Engineering School. And yeah, engineering just really seemed like a natural fit. Both of my parents were blue collar workers. Neither of them went to college. I was the oldest of 4 daughters. So we were really just figuring it out together. I picked the University of Pittsburgh. It was in my hometown. It was a good engineering school. Pittsburgh is considered the city of bridges. So I was surrounded by engineering. And then that's kind of where I landed, really. When it was freshman year, so freshman year, at least for the engineering curriculum at the University of Pittsburgh, is when you take all of the general classes. So everyone that wants to be an engineer takes all of the same classes freshman year. And then it's not really until the end of freshman year that you decide what path that you want to take within engineering. For me, civil and environmental engineering just really seemed like a natural fit, just giving my background and my interests. But it was really my experiences outside of the classroom that helped choose this direction and helped to solidify it. So many of you are probably familiar with a career fair. This is an activities fair. You may also be familiar with an activities fair. An activities fair is similar to a career fair, but rather than employers showing up, it is every club or every extracurricular activity that's on campus, and they're tabling and they're showcasing what they do, and they're trying to recruit new members. You may have something similar to this in high school now. I know I didn't, but I also didn't have this opportunity in high school. So times have changed a bit. So at these activities fairs, this is where I really discovered the possibility of engineering. This is where I discovered how broad and how versatile engineering really can be. So some of these organizations were actually on the slide that Eric just shared. And I really strongly encourage everyone to check out all of the different options that there are out there for these different clubs and activities. There's many organizations that are based on certain disciplines or based on certain backgrounds, based on certain interests that really align that can align your engineering background with what you are actually interested in. So for me, the ones that really resonated were ASCE, the American Society of Civil Engineers, SWE, the Society of Women Engineers, ESW, or Engineers for a Sustainable World, and then Engineers Without Borders USA, or EWB. So all of them had a really profound impact on my engineering education, but it was really EWB that resonated with me the most. And my experience with EWB is how I developed my why. So my why meaning, what is my purpose in engineering? Why was engineering the right career path for me? Why did I want to be an engineer? So let me dive a little bit deeper into that experience. So when I was a sophomore in college, I had the opportunity to work in partnership with a community in Ecuador. The community was called Tingo Pucará, and they were located way up in the Ecuadorian Andes. The community was made up of 28 homes, about 100 people, and they didn't have running water in their homes. So every day, in order to get water, the community members would hike down a mountain. It was 1,000 feet in elevation, and they would haul water from the river, carry it back up to the mountain to their homes. And for this community, you know, not having water meant taking hours out of their day to do something that we do in seconds just by turning on the tap. You know, the responsibility of hauling the water mainly fell on women and children. It was taking away precious time where they could be working, where the kids could be going to school, or even just pursuing other interests. And then, of course, you know, lacking water for proper hygiene and sanitation causes illness. It proposed health risks to the community. And there were just a lot of challenges that were associated with not having water at their homes, other than just the fact that they couldn't turn on the cap or the tap. So I was really fortunate to work alongside a group of professionals in the community to design a solution to get water to the homes. And won't go through the design in too much detail, but in summary, it consisted of a natural spring that was way at the bottom of the mountain. That spring source was collected in a spring box, and it was chlorinated at that point, and then it was gravity fed to a sedimentation tank. So similar to all that water that we were seeing, the dirty water where you guys had, where the sediment was kind of settling at the bottom after sitting there, that was the purpose of this sedimentation tank, was that the water flowed through it, and while it did so, those suspended solids were lowering to the ground. The water was then pumped up 1,000 feet up the mountain. So this picture here in the middle shows, this is actually the sedimentation tank on the right here, which is located down here at the bottom of the picture in the middle. And then that dirt path you can see is where we dug to bury the pipe to pump the water all the way to the top of the mountain, where it was in a storage tank. And then the storage tank was then gravity fed and distributed to the 28 homes. So that's a little bit of a summary of the system itself. The community had a big role in helping execute this project. Not only were they involved with the design, they helped with the construction. You can see women carrying pipes all the way down the hill. People were digging out for the tanks. It was really a team effort. And then a couple years later, the community had running water for the first time. So here's a picture of the community celebrating just that. And it's been almost 10 years now, and the system is still functioning as designed. The community is still operating it. And happy to say that the community now has, you know, water to their homes. So for me, you know, it was engineering that got that water to the tap. You just heard me explain all the engineering terms of the design of the system. But what I learned through my experience is that these projects are so much more than just engineering. There was, you know, the training of the community members. There was developing a water board so that they could collect the fees and make sure that they had the funds to operate the system. There was the actual operation and maintenance. There's the actual development of that payment structure. So there is so much more than just the engineering calculations that went into this project. And for me, most importantly, my kind of aha moment is when I realized that there are people behind every math problem that I was doing. It put meaning behind the math problems that I like to do. It shed a whole new light on the human element of engineering and just the importance that engineering has on humanity, human connection. And it's just so much more than just problem solving. There are real people behind these problems that we are solving. So when I graduated from the University of Pittsburgh, with a civil and environmental degree, as Eric mentioned, I also had a concentration in construction management and a focus on international studies. And I started working for a large national general contractor. I also co-opted with them or a similar company throughout college. So I gained that critical insight as a student. And then as a new hire, I started working in the building division, estimating and building commercial buildings. I was quickly relocated to Washington, D.C., and I worked as a project engineer on the construction of a high-end hotel, which is what you see here on the right. It was a really, really cool, really exciting project. It was a historic church that we were renovating into a hotel lobby area. And then where this picture is taken is going to be the construction of a new tower that would house the hotel rooms for the hotel. And then what you're looking at here is the earth retention structure. So we dug 50 feet below grade for the parking in the lower levels of the building. There was a lot of earth retention, making sure that we had to hold back all that earth to build up. And there also was a lot of water infiltration issues. You know, DC was actually built on a river. It was built on a swamp. So we had a lot of challenges with dealing with water on the job site and how we could move that water so that we can build the foundations that we needed to. I learned so much about engineering on this project and construction. But I think even more so, I learned a lot about myself as a person and myself as an engineer. You know, at many given times, not only was I the only female engineer on the job, but I was the only female on site out of maybe a couple hundred people. You can see here pictures on the left. These were my immediate coworkers. So it's really, you know, I learned firsthand the challenges that come with being a female or a minority in engineering. I learned that I had to work quite a bit harder to prove myself than my male counterpart. But I also learned how empowering it feels to overcome that. You know, engineering school kind of teaches you a lot about the calculations and the rules and the theories, but it also teaches you about problem solving. And for me, that problem solving combined with these experiences of being on projects and seeing things firsthand is really the most applicable thing when you go into the workforce. Let's see, I think that, you know, just to reiterate, I think that this job also kind of taught me what it meant to be a good engineer. Being a good engineer is a lot more than just being good at the technical things. It's really about the soft skills. It's about communication. It's about people management. And it's about connection. You know, it really, there's such a human element that goes into engineering. So I was really proud of that project. I was proud of my work. But I kept going back to that sense of purpose that I felt with my experience at EWB. And I was really just craving that human connection and that depth to engineering. But it really was all of those experiences combined, you know, the EWB, all of the clubs that I was in, my experience as a co-op, my job right out of school, all of those experiences combined where I discovered my why. And my why it is the people. It's my purpose in engineering is to use those skill sets that I developed in school, but to have a more direct impact on the quality of life of others, to make a more positive impact in the world, and really to engineer with empathy. to understand and share the feelings of others through engineering, which I think is something that often gets left out of the actual engineering profession. So that's where I got to where I am today at Engineers Without Borders, or EWB. When the hotel project ended, which lasted about 6 years, I decided to make the career shift to working at EWB full-time. So I'm going to share a little bit more about EWB and kind of the projects that I work on today. So first off, who is EWB? What is EWB? In short, EWB was founded in 2002, so over 20 years now, and we are a community engineering nonprofit organization. So what does community engineering mean? You might hear the term humanitarian engineering. It's very similar. Community engineering means that we partner with communities throughout the world who lack basic access to infrastructure. These communities are communities that face inequities and inequalities due to their economic status, their race, and just otherwise can't afford or access traditional for-hire services. And we're also a volunteer organization. So we have volunteers who are the ones that are partnering with the communities to advance the infrastructure needs. And by doing so, the volunteers are enhancing their worldview, and they're creating a human element to engineering that allows them to go out and be better engineers and be better global leaders. All the while, communities, we are ensuring that they are using their power to also build their skill sets and go out into the world to be better global leaders. And it's just so important to note that the communities are the experts of their own challenges. They have the expertise and the knowledge to solve their problems. And many times they often just lack that capacity or the resources to actually do so. And so that's why it's so important to note that we partner with the communities to help them advance their challenges. And we're not working for them to advance their infrastructure goals. It's really a partnership and a collaborative effort. And all of the projects are community driven, meaning that the communities come to us with their challenges and what they're trying to solve. And we don't show up in their communities and say, we're engineers and we think that this is what you need. Because like I said, they are the experts of their communities. They're the experts of their infrastructure. They're the experts of their challenges. I think that's just really, really important to note, because as engineers, we sometimes have the tendency to think that we have the answers to everything. And, some people, that might upset some people hearing that, but it's just not true. Engineers don't have the answers to everything. I mean, Eric just mentioned it. Where engineers are, it's not always right. There's no wrong answer when it comes to engineering. And if something isn't right, you just learn and you grow from it. So I think so much of being an engineer is more than just being right in problem solving. It's about, actively listening. It's about listening to these communities, listening to their needs. It's about partnership. It's about collaborating. It's so much more than just crunching those numbers. And it's really working with everyone together to find a solution that's best for all people involved. Not this one person, not you as the engineer, but making sure that the solution that you come up with is impacting all people and the environment involved around it. So let me give you a little overview of EWB. So this map shows where we are currently partnering with communities. We currently have 509 active community given projects. And this varies, at any given time, but it usually hovers around that 500 number. And we have community projects in 39 different countries and 29 different states and territories here in the US. You'll see in the top right, that orange, this little chart breaks down the type of our projects. Orange is water supply. So most of our projects are around water and water infrastructure. This can vary from communities getting water for the first time, like the project that I explained, or communities here in the US that are dealing with water violations and helping them get back up to standards and codes. We also have, let's see, we have over 200 chapters, volunteer chapters. So I mentioned that we are volunteer led. Our chapters are made up of both professionals and university students. As a high school student, you guys are definitely welcome to check out a local chapter, learn what their project is, learn what their involvement with EWB is like. And then those chapters, they're the ones that form project teams, and they work with our staff to partner with communities to improve their infrastructure and to move through the infrastructure projects. Yeah, so that's an overview of EWB. We have purposeful partnerships. I think just to reiterate, we really want to ensure that we are developing purposeful partnership, not only with communities, but with other NGOs, other nonprofits that are local to the area, that are the experts of the area, and really making sure that those partnerships are in place so that we are doing our work in the best possible way that we can. Yeah, so let's go over, you guys heard a lot this morning in the water access video about just why water access and why water security and why water treatment is so vital across the globe. So I'm going to touch on a couple more stats that feeds directly to the work that we do here at EWB. There are 748 million people across the globe that lack access to clean water. And also, as we heard this morning, water is not a finite resource. So how can we ensure that everyone has access to water, that needs access to water, while also making sure that our efforts to conserve and to preserve, this natural resource are paramount? It's a big challenge. A lot of our projects here at EWB are like the ones that I explained earlier on with the community in Ecuador, where community is accessing water for the first time. But in addition to water, we also do projects that are around school buildings, designing and building school buildings, designing and building bridges. We have latrine projects, we have solar projects, we have agricultural projects where we're working with communities to understand what their climate impacts are on agriculture and how they can, maybe adjust or enhance their agricultural practices to meet the climbing or the changing climate. So we do a little bit of everything that's infrastructure related. And then specifically here in the United States, zooming in on the area that we're maybe all most familiar with and in our backyards. In the US, there are 2.2 million Americans that lack access to safe water and sanitation. There are also 44 million Americans, I think that this stat was actually shared earlier, that have Safe Drinking Water Act violations. And then Native Americans are 19 times more likely than white households to lack indoor plumbing. So at EWB, we have a separate program called our Community Engineering Corps program that focuses on communities here in the US. Eric mentioned that's the program that I focus on my day-to-day. It's a partnership program of Engineers Without Borders, American Water Works Association, and American Society of Civil Engineers. So these are three organizations that at their core just deeply care about water and water infrastructure and infrastructure in the United States. So it's a really great alliance that we have that allows us to tap into volunteer networks and partner with communities in the United States that need engineering and can't afford or can't access it. They need a little bit more of a boost to move their project forward. So let me just give a couple project examples. This project here on the right, this picture, is a project that we have in partnership with an organization called Dig Deep. Dig Deep is working to provide families across Navajo Nation with access to water, among other things. That's just one of their projects. And they have a system on the nation to collect water from different watering points and haul them to the individual homes, where the homes then have plumbing, from these outdoor cisterns that go into their homes, and communities have running water in their homes for the first time, sometimes in a long time. And then, so we partnered with them to help provide a standard operating procedure to increase their water quality protocol so that they can ensure that water from the source to the homes is of the highest standard and care that you would expect for water here in the United States. So that's just one of the projects that we have. Another example, we worked with a small Black community in Maryland, in rural Maryland. Black households are twice as likely, 2 times as likely, more than white households to lack indoor plumbing and sanitation. So we partnered with a community that had a well collapse. There's about 16 homes on this well. Their well collapsed, leaving them without running water. So they were forced to haul water into their communities, which was not only very expensive for the community, but it was just not sustainable whatsoever. So we explored options with them, connecting to the local utility. While that seems like a no-brainer, regionalization, it wasn't feasible for this community. It was way too expensive, costing them millions of dollars that they didn't have. And it also would have included going under a highway. So it just wasn't a feasible solution. So we worked with them to develop a preliminary engineering report to drill a new well, and they were able to use that report and apply for grant funding. And then they received that grant funding, and they were able to drill the new well, hire an engineer to design the rest of the system, hire a local engineer to design the rest of the system. And now they have an improved water source all over again.
Natalie, I was just gonna say, American Senior High School has a student that wants to ask you a question. So they want it. They're popping up, and we have also some questions in chat. I'm not sure if you can see the chat, but I can relay them to you. But this gentleman has a question he wants to ask live. So go ahead.
Please, I would love.
What has been your toughest experience in your career?
I'm sorry, can you repeat that?
So what he was asking is, what has been your greatest challenge as a member of Engineers Without Borders?
That's a great question. I think that my biggest challenge as a member of Engineers Without Borders specifically is just seeing the need that is out there, seeing the need globally, and realizing that I definitely alone, or our organization alone, just isn't going to be able to match all of the needs. I think that is my biggest challenge. It's something that, I think about every day, is how can we how can we partner with the most communities to make the biggest impact, and also do so in a meaningful and respectful and ethical way. I think that has been my biggest personal challenge at EWB. I think my biggest challenge working in my career in general was, I shared a little bit of it, but just being a female engineer on a construction site had a big set of challenges that I really enjoyed overcoming. I felt very empowered by it, but it definitely it was hard. It took a lot of practice, it took a lot of growth, and it took some time to get to the point where I was able to have the confidence that I knew that I needed and deserved.
Well, we have one more question, okay, that came up as they were doing the activity.
Yeah.
And that question would simply be, how do you wrap your mind around the idea that the same water that is a part of you and that they've been using for drinking and everything else has been used for everything that water can be used for as long as water has been on this planet?
I'll tell you what, when I heard that dinosaur fact this morning, I was also, my mind exploded. It's crazy. I know that's what I learned, and that's what I do every day, but it is crazy to think about that the same water that we've had here has been here for billions of years. And I think it just, the thing that really resonates with me is just that every drop matters. If we can all do our part of thinking about not leaving the tap on when we're brushing our teeth, not leaving the hose running outside when you're watering plants, that is just what really sticks with me, is we want this water to also be here, you know, for the next, not only for our kids and our grandkids and their grandkids, but, you know, in the next billions of years, we're not going to have life without the water. So I don't know how I wrap my head around it. If anyone has any thoughts on it, I would love to hear, because yeah, it's crazy to think about it from that perspective.
So we have a question in chat that goes back to something you brought up, and I'm not sure if you want to get into these questions, but it says, do communities publish a clean water report, and how do you know if your drinking water is safe?
That is a great question. So most communities here in the US, most municipalities do produce a clean water report. And that will go through and it will highlight the testing procedures that they take, that they have, what their results were. It's a great question for communities that don't have that. You know, I definitely encourage, there are at-home tests, there are other things that you can do to ensure that the water in your tap is safe. I think that one of the other safest things that you can do is getting an additional filter. You know, Brita filters were talked about, the Life Straws. There are other home filters that can be used just to ensure that, you know, that extra level of security. But when water is coming from the local municipalities, and those treatment facilities are heavily regulated, they are heavily maintained by the operators, and you can feel safe about that water being safe drinking water. But you know, it's a great question. We've seen communities that have been impacted by non-safe drinking water.
We have it. Oh, go ahead, Mr. Cox.
Okay. Natalie, we have one more. One of the students really wanted to know, have you ever been in a situation where you had to filter your own water from a lake or a river supply? And what was the material that you found most effective to filter or clean out, okay, your water, and aside from, okay, just disinfecting?
Yeah, that's a great question. I will note that I'm very fortunate to have the privilege to grow up with safe drinking water my entire life. That it is a privilege, and I definitely recognize that. I have done a lot of backpacking and outdoors things where I was forced to drink water from rivers or streams or ponds. And the filter that I used in those situations was it's called a Sawyer filter. It's very similar to the Life Straw design. It has these fibers that have very, very small pores, like 0.01 micron or something very, very small, that doesn't allow any bacteria or any suspended solids to go through. So that's the type of filter that I've used in those situations.
All right. We have another question in chat. It says, is well water better or worse than other water sources?
That's a great question. Neither necessarily. You know, well water, Eric just showed that picture, the image of the well topping into the reservoir. You know, all water should be tested. It really just depends on where that reservoir is, what else the reservoir has come in contact with, what the other source water is. You know, source water can be springs, rivers, whatever that might be. I don't think, at least in my opinion, there isn't, you know, one that's better than the other. It really just depends on the actual source.
So we have another question, and says, we are in Florida and we often get boil water warnings after bad storms. Why do we have to do that?
That is a great question. I'm not familiar with Florida, but I know that in many situations, so when there are heavy storms, it tends to overflow the treatment systems and the treatment plants. Eric, you might have some more insight on what the specifics are in Florida.
Yeah, and I think that you're right on. I think it's when you do get overflow, I think sometimes the treatment plants, it goes beyond their design limit, I believe. And it's possible that you'll get more contamination as a result. And just to be safe, so that you're not drinking, you know, contaminated water, they want you to boil it to kill any bacteria. I think that's where you're going, Matt.
Yeah. Yeah, exactly. It just overflows the systems, and there can be more contact with surface water or standing water. And I think it's just as an extra precaution to ensure that there aren't any contaminants until the system gets back into its regular flows and regular servicing.
Well, thank you,
So
Eric,
many
for
great
hopping in there.
questions.
There's a lot of great questions. And then there's one that we get here at Engineering Tomorrow a lot that I think somebody asked in one of the forms that was submitted earlier. How are pro bono engineering projects funded?
Yes, that I did see that. So going back really quickly to our projects. So our international projects are set up a little bit different than our US projects. Our international projects are funded by the community and by fundraising efforts that are put on by our chapters here in the United States. So a lot of times those fundraising efforts will be individual donors, there'll be organizations, corporate partners, other kind of sponsors. And for international projects, the community always contributes to that cost as well. So they have a buy-in of at least 5% of the construction costs. And they are able to raise those funds either in their community or by reaching out to their local governments and receiving funding that way. For the United States work here, we really, what we strive to do is to provide a pro bono engineering report so that the communities can use that to tap into grants or to tap into other funding sources. So that really just depends on the project. But we also, as staff, are funded by government grants. So that's how I'm able to be here as a staff member. And that trickles down to our projects. Yeah, so I guess just to wrap things up, and then I'd love to answer some more of these questions. Just with a really quick story about when I was in college, there was a thing called AMA, or Ask Me Anything, on Reddit. I don't know if this still exists. It's probably something that's on TikTok now in a way cooler version of it. But pretty much what it was you could ask people that were going live at that time any question. And at this point, it was the CEO of EWB at that time who went live, and she was answering questions from anonymous people. And I asked a question that was kind of along the lines of, how does an inspiring engineer like me get to a position like you, the CEO of an engineering nonprofit? And her response was, one, find something that you're good at, and two, find something that you're passionate about, and then find the intersection. And so for me, it was engineering with empathy is that intersection. I was good at math. I was good at engineering. I was passionate about helping people, about human connection. And it's that engineering with empathy that was the intersection for me. And that's what got me to where I am today. So I would just encourage all of you to find your why. With engineering, you have the opportunity to make the world a better place, and the options are endless. So just wanted to just leave it with that. And I am happy to answer some more of these questions. And if I don't know the answer to them, the best thing you can do as an engineer is to admit that you don't know the answer and then work with someone to find that answer. So let's see what other questions we have.
Well, I don't know if you, St. Raymond's. Oh, no, that's not a question. They're just saying thank you. So let's see.
Thanks,
we have a lot of questions here. What is the
sorry, go ahead.
Nope, you go.
I was gonna say that I see one, do I work with engineers of other disciplines? Absolutely, yes. There is no such thing as just an engineering project that only works with one type of engineer. Everything touches all other aspects of engineers. So, if you think about, let's think about a building or a house, for example. You have a structural engineer designing the actual structure. You have a mechanical engineer designing the heating, ventilation, and air conditioning. You have a plumber or a water engineer that's designing the actual water and plumbing system. So that's just three. You have the foundation engineer, the geotech. Every engineering project touches all aspects of engineering. And me personally, yeah, I work with all different disciplines at all given times.
Yes. I think that's something that Engineering Tomorrow likes to emphasize is how it all takes a team, right? It's not just one person doing it, and it's all those interdisciplinary skills that are brought into the team. But I want to hop in and say, I think, Natalie, thank you for bringing the human element to our water treatment event today. I think you are inspiring and just an amazing example of a human being and bringing that human element to engineering, which is just so in line with Engineering Tomorrow's mission. And we're so proud and honored to have you participate today in our first event for the year. I think this was a fantastic event. I want to say thank you to all of our presenters who were here today. Eric Einset, our mentors. I want to say thank you to all the ET staff who was here to support our students throughout the day in those breakout rooms. An amazing, amazing day. I know that you guys had a lot. I see a lot of emojis of claps. Yes, these are amazing presenters, and we're so fortunate to be here with you all. We look forward to seeing you guys again. We have these events twice a month. Our next event is going to be Bridges on September 27th. We hope to see some of you there. And if not, tell your team